Let's say you want the computer to recognize the handwritten digit 9. The way computer looks at this is as a grid of numbers. Here I'm using -1 and 1. In reality, it will use RGB numbers from 0 to 255. The issue with this presentation is that this is too much hard-coded. If you have a little shift in digit 9, for example, 9 here was in the middle, but in this case it is on the left, and the representation of numbers just changes. It doesn't match with our original number grid, and computer will not be able to recognize that this is number 9. There could be a variation since it is a handwritten digit. There could be variation in how you write it, which will change the two-dimensional representation of numbers, and again you will not be able to match it with the original grid. So we use artificial neural network for this kind of case to handle the variety. In this deep learning series, we have already looked at artificial neural network video on handwritten digits recognition. If you have not seen that video, please make sure you see it so that your fundamentals on artificial neural networks are clear. In that, we created a one-dimensional array by flattening the two-dimensional representation of our handwritten digit number. And then we build a neural network with one hidden layer and output layer. And this dense neural network will work okay for a simple image like handwritten digit. But when you have a bigger image, let's say this little cute looking koala, the image size is 1920 by 1080. We have 3 as RGB channel here, one for red, green, and blue. In this case, the first layer neuron itself will be 6 million. If you have, let's say, hidden layer with 4 million neurons, you're talking about 24 million weights to be calculated just between the input and hidden layer. And remember, deep neural networks have many hidden layers. So this can go easily into like 500 million or 1 billion of weights that you have to compute. And that's too much computation for your little computer. See, my rabbits are getting electrical shock because it's just too much to do. So the disadvantages of using ANN or artificial neural network for image classification is too much computation. It also treats local pixels same as pixels far apart. If you have koala's face in a left corner versus right corner, it is still a koala. Doesn't matter where the face is located. So the image recognition task is centered around the locality. Okay. So if the pixels are moved around, it should still be able to detect the object in an image. But with ANN, it's hard. So how does human recognize this image so easily? So let's go into the neuroscience a little bit and try to see how we as humans recognize any image so easily. When we look at koala's image, we look at the little features like these round eyes, this black prominent flat nose, this fluffy ears, and we detect these features one by one. In our brain, there are different set of neurons working on these different features, and they're firing. They're saying, yeah, I found koala's ears. Yes, I found koala's nose, and so on. Then these neurons are connected to another set of neurons which will aggregate the results. It will say if in the image you are seeing koala's eye, nose, and ears, it means there is a koala's face in the image. Similarly, if there is koala's hands and legs, it means there is koala's body. And there are different set of neurons which are connected to these neurons which will again aggregate the results, saying that if the image has koala's head and body, it means it is koala's image. Same thing with handwritten digit 9. There are these little edges which come together and form a loopy circle pattern, which is kind of like a head of digit 9. In the middle, you have a vertical line, At the bottom you have diagonal line. Sometimes you don't have diagonal line at all, but we know that whenever there is a loopy circle pattern at the top, vertical line in the middle, diagonal line in the end, that means digit 9. So how can we make computers recognize these tiny features? We use the concept of filter. In case of 9, we have 3 filters. The first one is the head, which is a loopy circle pattern. In the middle you have vertical line. In the end you have diagonal filter. So we take our original image and we will apply a convolution operation or a filter operation. So here I have a loopy circle pattern or a head filter. This filter right here. The way convolution operation works is you take 3 by 3 grid from your original image and multiply individual numbers with this filter. So this -1 is multiplied with this one is multiplied with this one, and so on. In the end you get a result, and then you find the average, which is divided by 9 because there are total 9 numbers. And whatever number you get, you put it here. Now this particular thing is called a feature map. So by doing this convolution operation, you are creating a feature map. So you do it for the second round of 3 by 3 grid. Here I'm taking a stride of 1. You can take a stride of 2 or 3. Also, you don't need to have 3 by 3 filter. You can have 4 by 4 or 5 by 5 filter. And then you keep on doing this for your entire number. And in the end, what you get is called a feature map. Now the benefit here is wherever you see number 1 or a number that is close to 1, it means you have a loopy circle pattern. So this is detecting a feature. In the case of koala, this will be eye or a nose, because for koala, eye, nose, ears are the features. So by applying loopy pattern detector, I got this one here in my feature map. I also call it the feature is activated, it got activated here. For number 6, it will be activated in the bottom in this area. If you have 2 loopy patterns, the feature will be activated at top and bottom. If you have a number like this, it might be activated in different area. In summary, when you apply this filter or a convolution operation, you are generating a feature map that has that particular feature detected. So in a way, filters are nothing but the feature detectors. For koala's case, you can have eye detector, and when you apply convolution operation, in the result, see, you got these 2 eyes at this location. If the eyes are at a different location, it will still detect because you are moving the filter throughout the image. And they are location invariant, which means doesn't matter where the eyes are in the image, these filters will detect those eyes and it will activate those particular regions. Here I have 6 eyes from 3 different koalas and they are activated accordingly. Hooray! The hand of koala is in this particular region, therefore when I apply hands detector, it will activate here. Now for number 9, and I'm just moving between number 9 and koala so that the presentation is simple enough and you still get an idea. In case of 9, we saw that we need to apply 3 filters: the head, the middle part, and the tail. And when you apply those, you get 3 feature maps. So I applied 3 filters, I got 3 feature maps. And this is how these feature maps are represented if you're reading any online article or a book. They are kind of stacked together and they almost form a 3D volume. In case of koala, my eye, nose, and ear filters will produce 3 different feature maps, and I can apply convolution operation again. And let's say this time the filter is to detect head. By the way, the filter doesn't have to be 2D. It can be 3-dimensional as well. So just imagine this first dimension is representing eyes, and the second slice is representing nose, and third slice is representing ears. And by doing that filter, you can say that koala's head is in this particular region of an image. So you're aggregating these results using a different filter for head, and now this becomes a koala head detector. Similarly, there could be koala body detector. And now we got these two new feature maps, where this feature map is saying that koala's head is at this location and koala's body is at this particular location. Then we flatten these numbers. See, in the end, these are like 2-dimensional numbers. So we can flatten them. So to convert 2D array into 1D array. And then when you get these two array, just join them together. After you join, you can make a fully connected dense neural network for your classification. Now, why do we need this fully connected network here? Well, you can have a different image of koala. See, my koala is sleeping, he's tired. So now his eyes and ears are at a different location. Look at his ears. See, they're here. For previous image, the ears were in a different location. So that generates a different type of flattened array here. And you all know, if you know basics about neural network, that neural networks are used to handle the variety in your inputs such that it can classify those variety of inputs in a generic way. Here, the first part where we use convolution operation is feature extraction part. And the second portion where we are using dense neural network is called classification. Because the first part is detecting all the features, ears, nose, eyes, head, and body, etc. And the second part is responsible for classification. We also perform a ReLU operation. So this is not a complete convolutional neural network. There are two other components. One is ReLU, which is nothing but, if you have seen my activation video on the same deep learning tutorial series, we use ReLU activation to bring non-linearity in our model. So what it will do is, it will take your feature map and whatever negative values are there, it just replaces that with 0. It is so easy. And if the value is more than 0, it will keep it as it is. So you see, just look at the values. It's pretty straightforward. ReLU helps with making the model nonlinear because you are picking a bunch of values and making them 0. So if you see my previous videos in this deep learning tutorial series, you will get an idea on why it brings the non-linearity. Especially see the video on the activations in the same tutorial series. The link of this playlist is in the video description below. So you'll understand why ReLU makes it non-linear. But we did not address the issue of too much computation yet. My rabbits are still getting electrical shock. Do something. Because see, for this image size, if you are applying convolution, let's say with some padding, you're still getting same size of image. You did not reduce the image size. Sometimes people don't use padding, so they reduce the image size, but only little bit. So pooling is used to reduce the size. The main purpose of pooling is to reduce the dimension so that my computer doesn't get this shock, you know. So the first pooling operation is the max pooling. So here you take a window of 2 by 2 and you pick the maximum number from that window and put it here. So here, check this yellow window, 5182. What is the maximum number? 8. So put 8 here. Here, what is the maximum number? 9. So put 9 here. Similarly, here maximum number in green window is 3. So put 3. So you take the feature map, apply your pooling, and generate a new feature map after the pulling. But the new feature map is half the size. If you look at the numbers, you have reduced your 16 numbers into 4. So it's too much saving in your computation. So how it will look for our digit 9 case when you apply max pooling? Well, you can do a stride of 1. In this case, we did 2 by 2 window and stride of 2. Stride of 2 means once we are done with this window, we move 2 points further, 2 pixels further. In this case, we can do one stride. See, this is one stride. You get an idea. And we keep on taking max. And this is what we get. When our number is shifted, so see, this is the original number where we got this max pulling map. When number is shifted, you get this pulling map. So still you are detecting the loopy pattern at the top. So max pulling along with convolution helps you with position invariant feature detection. Doesn't matter where your eyes or ears are in the image, it will detect that feature for you. There is average pulling also. Instead of max, you just make an average. See, 5 and 1, 6 and 2, 8, 8 and 8, 16. 16 divided by 4 is 4. So, but max pulling is more generally used, but sometimes people use average pulling also. So benefits of pooling, number one, obvious. It's reducing your dimension and computation. The second benefit, it reduces overfitting because there are less parameters. And the third one is model is variant tolerant towards variation and distortion. Because if there is a distortion and if you're picking just a maximum number, you are capturing the main feature and you are filtering all the noise. So this is how our complete convolutional neural network looks like. In that, you will have typically a convolution and ReLU layer, then you will have pulling, then there will be another convolution ReLU pulling. There could be n number of layers for convolution and pulling, and in the end, you will have fully connected dense neural network. In this particular case, the first convolution layer is detecting eye, nose, and ears. Many times you will start with the little edges. You don't even start with eye and nose, but here for the simplicity, I have put them. But usually you'll start with edges, then you go to eye, nose, ears, then you go to head and body, and then you do flattening. Again, anything on the left hand side of this vertical line is feature extraction. So the main idea behind convolutional neural network is feature extraction, because the second part is same. It is a simple artificial neural network. But by doing this convolution, you are detecting the features. You are also reducing the dimension. There are three benefits of convolution operation. The first one is connection sparsity reduces overfitting. Connection sparsity means not every node is connected with every other node like in artificial neural network, where we call that a dense network. Here we have a filter which we move around the image, and at a time we are talking about only a local region. So we are not affecting the whole image. The second benefit is convolution and pooling operation combined gives you a location invariant feature detection, which means koala's eye could be in the left corner, in the right corner, anywhere. We will still detect it. Third is a parameter sharing, which is when you learn the parameters for a filter, you can apply them in the entire image. The benefit of ReLU is that it introduces non-linearity, which is essential because when we are solving a deep learning problems, they are non-linear by nature. It also speeds up training and it is faster to compute. Remember, ReLU is you are just doing one check whether the number is greater than 0 or not. If it is greater than 0, keep the number, less than 0, make it 0. The benefit of pooling is that it reduces dimension and computation, it reduces overfitting, and makes the model tolerant towards small distortions. How about rotation and thickness? Because by itself, CNN cannot handle the rotation and the thickness. So you need to have training samples which have some rotated and scaled sample, some thick samples, some thin samples. And if you don't, you can use data augmentation technique. What is data augmentation? Let's say for handwritten digits, you take your original data set and then you pick few samples and then you rotate them manually, or you make them larger or you make them smaller, thicker or thinner, and you generate new samples. By doing that, you can handle rotation and scale in convolutional neural network. Once again, here is a quick summary of what is convolutional neural network. You can take a screenshot of this image, put it at your desk if you're trying to learn CNN and a computer vision. To summarize, you take your input image, then you apply convolution operation and ReLU, then you apply pulling, again convolution, ReLU, pulling, and you can do this n number of times. After that, the second stage is classification, where you use densely connected neural network. Now, very important thing to mention here is these filters, the network will learn on its own. In previous presentation, we saw that we applied those filters by hand, but this is the beauty of convolutional neural network, that it will automatically detect these filters on its own, and that is part of the training. So when the neural network is training, or when the CNN is training, because you're supplying thousands of koalas images here, using that, it will use backpropagation and it will figure out the right amount of filters. It will figure out the values in this filter, and that is part of the learning or the backpropagation. As a hyperparameter, you will specify how many filters you want to have and what is the size of each of the filters. That's it. But you do not specify the exact values within these filters. The network will learn those on its own. And that is the most fascinating part about neural network in general. In next few videos, we will be doing coding using convolutional neural network, and we'll be solving variety of computer vision problems.